Hi everyone, I hope everybody is doing great, and today let's go over the key of the midterm examination for analysis of algorithms for spring 2025. And we have 5 questions, and let's go over them one by one. So in the first problem we have two algorithms A1 and A2, and for A1 we have A of n is equal to pnq plus 1 minus p into n square, and for A2 we have pn plus 1 minus p into n cube. So whenever we have functions given like this, we need to understand that they represent the time complexity of each of the algorithms. Okay, so here p denotes the probability, and of course everybody knows that probability lies between 0 and 1. And so let's look at the questions. A. Solve for the value of p when A2 will execute fewer instructions than A1 when n is a large value. So let's just assume that n is a large value and solve for value of p when A2 will execute fewer instructions. So obviously we will write down A2 is less than A1. That is because if the time complexity of A2 is lesser, then only it's going to run fewer instructions. So if we write A2 is less than A1, I want you to look at the PDF here, and this is the key, official key, and we are going to simplify for P. So I want you guys to look at this step right here. We can see that P into n minus 2n cube plus n square is less than n square minus n cube. Now in the left side we have a negative sign before the n cube, and on the right side we can see that n square minus n cube. So here we are subtracting the larger term from the smaller term, and even on the left side we have the negative sign for n cube, which is the highest value there. So we can see that both of them are going into negatives, and whenever there is an inequality and both of the terms have negatives in them, the inequality switches. Okay, so whatever was less than until now it's going to be a greater than symbol. So p greater than n square minus n cube by n minus 2n cube plus n square right here. So from there we are going to continue. We got a basic initial equation for solving p. Let's look at the second question. Based on part A, find values of p when n is equal to 100 and when n is equal to 1000. So we already have the p value. Now let's solve for p when n is equal to 100. We are just going to substitute those values right here, and if you have a calculator and if you calculate, we are going to get these values. Let's look at the third one. Based on part B, what can you conclude is the value of p when A2 has fewer instructions when n is equal to 1,000,000. So if you observe carefully in the B part, when n is equal to 100, the value of p was 0.4975. And when it was 1000, it went up to 0.49975. So as we increase the value of n, we can observe that the probability is also increasing. So when it goes up to 1,000,000, the n value, the probability p will also get even closer to 0.5. Let's look at the next one.
If p has a value equally likely anywhere between 0 and 1, which algorithm will run fewer instructions the next time we run them both on the same dataset? So what you need to understand here is that we cannot exactly say which algorithm will run faster just by knowing that it's between 0 and 10. Okay, in the first algorithm, if you observe here, in the first algorithm, the value p is the coefficient of the larger term n cube. So if the p value is higher, this whole algorithm is going to be higher. And
in the second value, you have 1 minus p into n cube. Then if the value of p is higher here, then this whole coefficient is going to be a smaller value because we are going to subtract it from 1. And since it is the coefficient of n cube, the whole A2 will be less. That is if probability is greater. But if we have p value lesser, then we can say that 1 minus p is going to be greater, and since it's the coefficient of n cube, this is going to matter a lot, and A2 will run faster and A1 will run slower. So that's what has been written here. If P is greater than 0.5, it is bad for A2, and A2 will run fewer instructions. If P is less than 0.5, then it's good for A2, so A1 will run fewer instructions. So that's that, and let's go to the next question. In the next question, we have been given a recurrence relation. It is in the form of T of n is equal to 2T of n by 2. So it's like a basic problem, and it is in the form, we can say, of AT of n by b plus f of n. We will talk more about this form and why it's so useful in the master method and all, but let's just look at the questions. So we have find T of n by 2 and T of n by 4. We just need to plug in those values here. If you observe, we just need to substitute these values here, and we'll get substitute n by 2 in n here, and you'll get 2T of n by 4 plus 2n. Substitute n by 4 and you'll get 2T of n by 8 plus n. I'll just show you how we got it. If you want, 2T of, let's substitute n by 2 by 2 plus 4 into n by 2, and we'll get 2T of n by 4 plus 2n. And similarly, if you substitute 2T of n by 4 by 2 plus 4 into n by 4, you are going to get 2T of n by 8 plus n. So that's how we got it. And let's go to the next question. Use repeated substitution as we did in class, and expand the T of n to 3 substitutions, generalize for I times, and solve the closed form. What you need to understand here is that the reason why we use repeated substitution is to find a closed form for the given recurrence relation. If you observe in the question right here, it is in the form 2T of n by 2 plus 4n. So for the equation that represents T of n, it again has an n value here, and it again has, this is also a recurrence relation. But if we are going to find a closed form, it shouldn't be a recurrence relation, it should be just a plain equation. So we don't need something like T in the equation. So to eliminate this, we are going to keep substituting this a couple of times and see what we can deduce from it. So repeated substitution, this is how it is done. Here you have the n value. T of n is equal to 2T into n by 2 plus 4n. So in the value of this n, let's substitute n by 2 and see what we can do. So we know that T of n is equal to 2T of n by 2 plus 4n. So let me just write it like this. 2 into T into, how much would be T of n by 2 here? T of n by 2, I think it can be written like 2T of n by 2 plus 4n by 2 plus 4n. What I just did is substitute n by 2 in this equation, and from there I'll get this equation. So that's like 2T of n by 4 plus n by plus 2n plus 4n, and here I have n by 4 again, T of n by 4, and that I can again substitute and get this 2T of 2 into 2T of n by 4 by 2 plus 4n to n by 4 plus 2n, sorry, plus 4n. Now let us simplify this a little. 8 into t of n by 8 plus 4n plus 4n plus 4n. So we can write 8 as 2 power 3 into t of n by 8 plus 3 into 4n. So what you need to remember here is that we did this repeated substitution 3 times here. So when we repeatedly substituted it 3 times, we got 2 power 3 t into n by, or maybe we can write this as this too. Two power 3. And so if we observe, if we did it 3 times, we got 2 power 3. And if we do it n times, we'll get 2 power n maybe. We have also been given that in the base case, t of 1 is equal to 0. So what we need to do is we need to try to substitute a value here and get this whole thing to come to 0 so that we can substitute 1 here. So let me try to do that. I want so before I do that, we can all agree that if I did this 3 times, I got 2 power 3. So if I did it I times, if I did this whole thing I times, I would get 2 power I t into n by 2 power I plus I into 4n. So if I want this whole term to come to 0 or 1, not 0, if I want this to come to 1 because t of 1 is equal to 0, if I want that to come to 1, I could just substitute 2 power I in the numerator here. So I could write n is equal to 2 power I, and by writing that, I would become equal to log n base 2, and here what would it become? 2 power I into t power 0, t power 1 plus I value is log n, so log n base 2 times 4n. So this whole term comes down to 0 and we are left with log n base 2 times 4n. So we can say that this finally comes down to 4 times n log n. So this is the closed form for this reconciliation. I know it's a big one, but still, yeah. And we can easily deduce from here that the complexity of this algorithm is like theta of n log n, because that's what we got here. Let's move over to the next problem, and we have t of n is equal to 2t of n by 3 plus 2t of n by 6 plus n. So what we need to understand here is that the coefficient before t, the value here, which is supposed to be the value of a, this will determine how many branches we are going to have. And the denominator here is going to determine by what size we are going to cut the problem size into. So since we have a coefficient 2 here, we will cut the whole problem into 2 branches of n by 3 and 2 branches of n by 6. And this right here is called work. It's called the actual work done on the 0th level. If this was 2n or something like that, I would put a 2 here, but it's just n, so I'm going to stick with n here. We are going to have to draw a recurrence tree, and let's do that. As I said, the coefficient here will determine how many branches there are. So there are 2 branches of n by 3. So as you can see here, let me just show through the PDF here. So here you can see that we have 2 branches of n by 3, and then again we have 2 branches of n by 6. If we compute the total work done in each level, in the 0th level obviously the work is n because f of n is n, and in the first level if we add up n by 3, n by 3, n by 6 and n by 6, that is going to be n by 3 plus n by 3 plus 2 into n by 6, that is 3. That is 3 into n by 3, right? So that's going to be just n. So in the first level, the total work done is n. And we can see that each of the branches is again getting divided as per this branching. So if the problem size n by 3 goes into this recurrence relation, it's going to produce n by 3 times n by 3, that's going to be n by 9, again n by 9. We have n by 6 times n by 3, that is n by 18, again n by 18. So in this way we can draw the whole recurrence tree, and this here is going to be the second level of the recurrence tree. And after putting in all the values, if you try to compute the total work done in the second level, it is going to come up to n again. Add up all these values and you will again end up with the total work done n. So that is basically how you draw the recurrence tree. Let's go to the next questions. So according to part A, is the work increasing or decreasing geometrically or staying the same? We can clearly see that the work in each level is staying the same. So the work is going to stay the same. Can this recurrence be solved by master method? So, okay, this is another big doubt to many people. Can we solve something by master method or not? If we have a recurrence relation that is in this form, AT of n by b plus f of n. If a recurrence relation is in this format, we will be able to solve this using master method, otherwise no. You have to remember this blindly. If the recurrence relation is in this format, we'll be able to solve it using master method, otherwise no. Here this A is the branching factor and B actually cuts down the problem by B each time, problem size. And f of n is the actual work done, and f of n you can also say is the work done at the 0th level. So let's look at this equation right here. Is the total T of n recurrence relation in this form? I know that if just considering this and this, you might think it is in the same form, but keeping the whole equation in consideration, we have another term here. So the b value here, we have two different values. So this is not in this form, and we cannot solve this using the master method. Again, okay, what is the height of the leftmost branch and rightmost branch? So look at here, we can see that this tree has to come to unity at one point or the other, and it will come down. It will go down like this, and this will go down like this. But if you see here, if we have this and we have this, one of the branches is going to come down to unity faster than the other, because on one side it is getting divided by 3 and on the other side it is getting divided by 6. So the height of the branch here and here is different, not the same. And you have to remember that if we are cutting down a problem, for example say n, if we are cutting down this problem by 3 every time, how many times do you think we can cut the problem n by 3 before we come to unity? And the answer is log n base 3. If you need to know how many times you can cut down the size of a problem by 2 before you reach unity, the answer is log n by base 2. So if we are going to cut down a problem by 3 before it comes to unity, you can cut it down log n base 3 times. So the height of the leftmost branch is going to be the leftmost branch is going to be log n base 3, because we are cutting down by 3 in the first one, and on the second side we are cutting it down by 6, so the height this side is going to be log n base 6. Find the theta complexity by extending the tree to a greater height from part C. We can observe here that the work done in each level is n. So if we want the total work done throughout this whole span of the tree, we need to understand how many levels there are, and we need to do number of levels into n to get the total work, right? So we need to know how many total levels there are, and we need to calculate n into n. But the left side is log n base 3 and the right side is log n base 6. And no matter which side you consider, if you take the left side, let's say it is n times log n base 3, and on the right side it is n times log n base 6. It doesn't matter because all logs are proportional, and you will end up with the total time complexity of n log n. Let's move over to the next question. So coming over to the master method, and this is one of the most important problems that you will encounter in this course. So if we need to be able to solve a problem using master method, we already saw that it needs to be in the form T of n is equal to at into n by b plus f of n. If you observe, all of the questions given here are in this format only, and in the master method what we are trying to do is we are going to look at the value of a and look at the value of b and f of n and see where the most amount of work has been done. And by looking at the total work that has been done, we will try to assess the theta complexity. We need to compare, one rule of thumb is that we need to compare n power log a base b with f of n. So let's look at the first problem. T of n is equal to 8t of n by 2 plus n cube. So here a is equal to 8, b is equal to 2, and f of n is equal to n cube. So let's substitute and let's first find n power log a to the base b. N to the power log a to the base b is equal to n to the power log a to the base 2, that is n to the power cube. So we can observe here that n to the log a to the base b is equal to f of n, because both of them are n cube and n cube. And you need to understand that whenever we encounter such problems, I mean, when the f of n value is same as n to the power of log a to the base b, you can say that it looks like this. This is 0th level, this is first level, this is second level, this is third level, and like this. And when the work done here is n cube, right? So this is n cube. What we are basically calculating is the work done by calculating n to the power log a to the base b. We are calculating how much work is done at the bottom level. So since both of them are equal, we can say that at 0th level it is n cube, and even at the bottom level it is n cube. And when the work done is staying the same throughout each of the levels, what we need to do to compute the overall work is just multiply n cube into number of levels. And you know how many levels there are? N cube into log n base 2, because that's how many times we can cut this problem size before it reaches unity. So whenever n power log a to the base b is equal to f of n, we can say that the theta complexity is equal to n power log a to the base b times log n. Let's go to the next problem, and we have n power log a to the base b is equal to n power log 4 to the base 2, that is n square, and we have t of n or f of n is equal to n cube. So we can obviously see that n cube is bigger than n square, and the theta will be automatically equal to n cube, the biggest one out of them. Let's go to the next problem, and we have f of n is equal to n square, and n to the power log a to the base b is equal to n to the power log 5 to the base 2, which is equal to n to the power 2.32. And out of n square and n power 2.32 is going to be higher, so the theta complexity will be n to the power 2.32. And the next one is an interesting problem, because we are getting f of n, we have the value n log n, and we have n power log a to the base b is equal to n. So whenever we have f of n value, already equal to n log n, but we get n to the power log a to the base b is equal to n, we need to check for the value of n itself. And if we already have a log n, the theta complexity will be n times log n to the power 1 plus 1. If there is already a power 1 here, we are going to add 1 to it, and we are going to make it 2. Let's look at the last problem. So we need to prove that n cube plus 2n is divisible by 3 for every positive integer n. So let us take the basis n is equal to 1, and if n is equal to 1, obviously we can substitute, and we're getting the value 3, and 3 by 3 you know is 1, so it is divisible by 3. What we are going to do is we are going to assume that for every integer j which is less than n, this is going to be divisible by 3. So we'll just substitute j in the place of n, and we will say that is divisible by 3. We are not saying that n cube plus 2n is already divisible by 3, but we are just saying that for everything that is less than n, we will assume that it's true. we know that j is less than n, so we can write j is equal to n minus 1. And let us compute the value. So we know that if we substitute n minus 1 in this given thing, it is going to be divisible by 3. We just know it because we assumed for every value less than n, it's going to be true. So we know that p of n is equal to n cube plus 2n, and we know that p of n minus 1, we need to calculate this by substituting n minus 1 in this value. After we get p of n minus 1, we are going to subtract p of n minus 1 from p of n, and we are going to get a value. Let us suppose that we have a multiple of 3, like we have multiples of 3 as in 3, 6, 9, 12 and 15. What if you took 9 and you added it with a multiple of 3 into x? X could be anything. X could be 1 or 2 or 3, anything. If you, let's just say x is equal to 3, and then this would be 9 plus 3 into 3, that is 9 plus 9 is equal to 18. So if you add a multiple of 3, another multiple of 3, like whatever it be 9 or 15 or anything, if you add a multiple of 3 with another multiple of 3, you just know that it is going to get you another multiple of 3. So let's look at this. We subtracted p of n minus 1 from p of n, and we ended up with a value which we observed is divisible by 3. So since we know that p of n minus 1 is divisible by 3, and we are adding this subtracted term, here we need to prove for p of n, but we know that p of n minus 1 is divisible by 3. If this is divisible by 3, and by adding a 3 multiple like this is giving us p of n, that must mean that p of n is also a multiple of 3. So that is how we prove it. I hope you understood all the solutions, and if you have any more doubts, we can discuss them in the review session.